Right now, you are standing on a sphere hurtling through the void at nearly 1,600 kilometers per hour. Yet the room around you is silent. Your coffee sits perfectly still in its cup, showing no ripples from the violent velocity of the planet beneath it. In the time it took you to hear these first few sentences, you have already traveled roughly 150 kilometers through the galaxy. You are a passenger on a cosmic machine that has been moving for 13.8 billion years without a single second of rest. Everything you see, the stars above, the atoms in your hand, and even the fabric of space itself, is twisting through the universe at unimaginable speeds. And still, you feel nothing. No shaking, no roaring wind, no blurring horizon. You are trapped inside a universal choreography where stillness may be the only illusion that truly exists. But the question is why? Why did the vacuum of space, the ultimate emptiness, choose motion over silence? Why does everything in the cosmos spin, orbit, rotate, and circle endlessly through the dark? Why didn't the universe simply drift in a straight line forever? If the invisible forces acting on your body right now leave you unsettled, then you are in the right place. And if you enjoy deep investigations into the hidden mechanics of reality, subscribe now, because the search for the universe's very first nudge begins now. To understand why your world is turning, we have to start with a difficult truth. There is no such thing as a still object in the universe. Perfection, in the form of absolute immobility, is a myth. Take a simple ball, a tennis ball or a smooth stone. If you toss it into the air, it will follow a predictable curve. Gravity will pull it down. But if you look closely, that ball is almost certainly spinning. Even if you try your hardest to release it perfectly, it will rotate. This is because perfect symmetry does not exist in our reality. When you throw that ball, your fingers do not release it with perfectly equal pressure. One finger might linger for a microsecond longer than the others. The air itself might push against one side of the felt more than the other. This tiny, microscopic imbalance creates what physicists call an off-center force. And in the mechanics of our universe, an off-center force has only one possible result: rotation. This simple domestic fact, the way a ball leaves your hand, is the exact same principle that built the solar system you live in. Roughly 4.5 billion years ago, there was no sun, there were no planets. There was only a ghost, a solar nebula. This was a cloud of gas and dust light-years wide. To give that scale a human face, that is roughly 9.4 trillion kilometers of cold hydrogen and the frozen shrapnel of dead stars. This cloud was not a silent, peaceful place. It was turbulent. It was messy. Its different parts were moving in different directions at different speeds. Some parts were being nudged by the shockwaves of distant dying stars. Other parts were being pulled by the gravity of passing molecular clouds. Because of these random nudges, the cloud had a tiny, collective twist. It was barely perceptible at first, a slight preference to move one way rather than the other. But then gravity began to do what gravity does. It began to pull the cloud inward. This is the moment where we encounter the first unbreakable law of the investigation: the conservation of angular momentum. Angular momentum is a technical term for a simple concept. It is the measure of an object's rotational persistence. This is confirmed science, not speculation. And the law says that once a system has this twist, it cannot be destroyed. It can only be concentrated. You have likely seen this at a skating rink. When a figure skater begins to spin with her arms outstretched, she moves slowly. But the moment she pulls her arms in toward her chest, her rotation speed explodes. She hasn't added any new energy. She hasn't been pushed by anyone else. She has simply moved her mass closer to her center of rotation. The solar nebula did the exact same thing. As gravity crushed that light-year-wide cloud down into the size of our solar system, that tiny original twist was amplified. The cloud didn't just get smaller, it began to scream with velocity. What was once a lazy, drifting fog became a violent, whirling vortex. But as it spun faster, a complication arose. Gravity was pulling everything toward the center, trying to crush the nebula into a single, unmoving point. If gravity had won, you wouldn't be here. The universe would be a collection of silent, dark dots. However, the rotation created a counterforce. As the cloud spun, material at its equator began to feel a centrifugal push outward. This is the same force that pulls you toward the door of a car when it takes a sharp turn. This push outward balanced the pull inward. The result was a protoplanetary disk. Instead of collapsing into a sphere, the cloud flattened out into a spinning frisbee of matter. In the center, the pressure became so intense that the hydrogen ignited and our sun was born. But in the outer parts of that disk, the leftover dust and gas were still trapped in that original, inherited rotation. This is the key to your existence. Every planet in our system, including the one you are sitting on, was formed inside this spinning disk. Think of it as a cosmic pool table. Inside that disk, pebbles were colliding, dust grains were sticking together, but in space, things almost never collide head-on. Just like a billiard ball hit on its side, every collision in that early disk added more spin to the growing planets. Earth is essentially a 6 sextillion-ton fossil of a 4-billion-year-old twist. Your 24-hour day is not a random number. It is the specific result of how many times our young planet was kicked by passing rocks during its birth. This is established data. We can measure this inherited nudge even now. Because there is no air in space, no friction to act as a brake, that original motion has nowhere to go. The Earth continues to turn today simply because there is nothing in the vacuum of the void powerful enough to tell it to stop. But here is the first major complication in our discovery. If everything inherited its spin from that one original disk, you would expect everything in our solar system to spin the exact same way, like a perfectly synchronized clock. But it doesn't. Venus spins backward, Uranus rolls on its side like a bowling ball. And some galaxies are spinning so fast that by all the laws of known physics they should be flying apart into the darkness. This tells us that the inherited nudge is only the first layer of the story. The universe didn't just start with a twist, it has spent the last 13 billion years trying to survive it. We have established that you are moving. We have confirmed that the Earth, the Sun, and the galaxies are all passengers in a frictionless void carrying a twist they inherited billions of years ago. But this leads us to a much deeper, more unsettling question. Why does the universe allow spin to exist at all? In a world of logic and order, you might expect the universe to prefer stillness. You might expect that after the chaos of the Big Bang, everything would have eventually settled into a quiet, unmoving equilibrium. But it didn't. And the reason for this isn't just a matter of leftover motion, it is written into the very laws of reality, a concept physicists call symmetry. To understand this, we have to look back to 1915. While the world was consumed by the fires of the Great War, a German mathematician named Emmy Noether was quietly proving a theorem that would change our understanding of the cosmos forever. This is not speculation. Noether's theorem is considered one of the most beautiful and profound pieces of mathematics in human history. What she discovered was a bridge. She proved that every conservation law in physics, the rules that say things like energy or momentum cannot be destroyed, is actually caused by a specific symmetry in the universe. If you want to understand why your coffee cup doesn't spontaneously start spinning on its own, or why the Earth hasn't stopped its rotation after 4 billion years, you have to understand what Noether called rotational symmetry. Imagine you are standing in a perfectly dark room. You have a laboratory table in front of you with a simple experiment, perhaps a swinging pendulum or a set of colliding billiard balls. You run the experiment and record the results. Then you rotate the table 90 degrees to the north and run it again. Then 180 degrees to the south. The results are identical. This is what we mean by a directional democracy. The universe does not care which way you are facing. There is no up or down in the vacuum of space. The laws of gravity, electromagnetism, and nuclear force are exactly the same whether you are pointing toward the center of the galaxy or away from it. This is established data, measured directly in laboratories and through deep space telescopes. Noether's theorem tells us that because the universe has no preferred direction, because it is symmetrically indifferent, a property called angular momentum must be conserved. It is a mathematical necessity. If the universe did have a preferred direction, if physics worked differently when you faced east, then spin would eventually fade away. It would leak out of the system. But because the universe is a democracy of directions, once a twist is started, the universe has no way to delete it. To stop the Earth from spinning, you would have to break the rotational symmetry of the entire cosmos. You would have to make west fundamentally different from east at the level of subatomic particles. This is the deeper layer of our investigation. Spin isn't just a motion. Spin is the physical manifestation of the universe's refusal to pick a favorite direction. However, this is where our discovery meets its first massive complication. If the universe is truly a perfect democracy, if every direction is equal, then we should see a perfect balance in the cosmos. We should see exactly as many galaxies spinning clockwise as we do counterclockwise. In a perfectly symmetric universe, the total spin of everything should add up to exactly 0. But it doesn't. This is the law gap that mainstream science is only just beginning to confront. Multiple independent teams analyzing data from large-scale surveys like the Sloan Digital Sky Survey have noticed a subtle, haunting asymmetry. When we look at thousands of spiral galaxies across the sky, there appears to be a 1% to 2% excess of galaxies spinning in one specific direction over the other. A 1% difference might sound small, but on a cosmic scale, a 1% preference is a catastrophe for our understanding of symmetry. It is like flipping a coin 1 billion times and having it come up heads 10 million more times than tails. It shouldn't happen by chance. This suggests that the universe might have a handedness. This brings us to a concept known as parity violation. For decades, physicists believed in p-symmetry, the idea that if you built a mirror image version of the universe, it would behave exactly like ours. If you replaced every right-handed twist with a left-handed one, the physics should be identical. But in 1956, researchers looking at the weak nuclear force, the force responsible for radioactive decay, found something that shocked the scientific community. They found that subatomic particles have a preference. They found that the universe is left-handed. This is not a metaphor. Subatomic particles, like neutrinos, only ever spin in one direction relative to their motion. Their mirror images simply do not exist in our reality. The directional democracy we just discussed has a hidden, secret bias, and this bias isn't just limited to the cold reaches of space, it is inside you. Every single piece of life on Earth, from the bacteria in your gut to the neurons in your brain, is built from left-handed molecules. If you were to create a right-handed version of an amino acid in a lab, it might look identical to the one in your body, but your cells wouldn't know what to do with it. It would be biologically inert or potentially toxic. This is the handedness conspiracy. The rotation of the galaxies, the spin of the first atoms, and the spiral of your own DNA are all linked by this same mysterious preference. We are living in a universe that isn't just spinning, it is leaning. Why did the Big Bang choose a side? If the laws of physics are symmetric, why is 1% of the cosmic rotation left over? Some theorists suggest that this is a fossil record of the very first second of existence. They believe that before light even existed, the universe underwent a period of inflation, a moment where space expanded faster than the speed of light. In that violent expansion, tiny quantum fluctuations, little whirlpools in the fabric of space, were stretched out to the size of galaxies. If those first whirlpools had a slight bias, that bias would be frozen into the structure of the universe forever. So when you look at the stars tonight, you aren't just seeing points of light, you are seeing the survivors of a cosmic choice. You are seeing a universe that, for a reason we still cannot fully explain, decided that one direction was slightly better than all the rest. But as we go deeper into this investigation, the mystery doesn't just stay at the level of direction, it moves into the very fabric of reality itself. Because when rotation becomes extreme, when we move away from the gentle spin of the Earth and toward the violent crushing centers of dead stars, spin stops being a motion and starts becoming a time machine. Up to this point, we have treated rotation as something that happens inside the universe. We have looked at how planets and stars turn within the vacuum of space, but as we move into the extreme layer of our investigation, we encounter a point where the distinction between the object and the space around it begins to dissolve. To understand this, we have to travel to the remnants of dead stars, places where gravity has won the battle against matter, and where spin has reached a frequency that challenges our understanding of reality. Imagine a star roughly twice as massive as our Sun. Now imagine that entire mass being crushed, not into the size of a planet or even a moon. Imagine it being squeezed until it is only 20 kilometers wide. 20 kilometers. This is a distance you could drive across in a car in less than 20 minutes. This is the size of a small city. Yet inside this narrow radius, the universe has packed a mass so dense that the atoms themselves have shattered. This is a neutron star. To grasp the density we are talking about, we have to move from cosmic scales to a domestic analogy. If you were to take a single teaspoon of the material from this star and bring it back to Earth, that small amount of matter would weigh roughly 1 billion tons. That is the equivalent of a massive mountain, or every car on the planet combined, compressed into something you could hold in the palm of your hand. This is established data, measured through the observation of starlight and the gravitational effects these objects have on their neighbors, but it is what happens next that changes everything. Because this object was once a massive, slowly turning star, the law of conservation of angular momentum dictates that as it shrank, it had to spin faster, much faster. We have measured neutron stars known as pulsars that rotate at 716 times per second. 716. In the time it takes you to blink once, this object, this sphere weighing more than our entire solar system, has completed over 200 full rotations. The surface of the star is moving at a significant fraction of the speed of light. At these speeds, rotation stops being a simple movement and begins to warp the environment. This is where we encounter the lens-Thirring effect, or what physicists more commonly call frame dragging. This is not speculation, this is a confirmed phenomenon of general relativity. Think of space not as an empty void, but as a physical fabric, like a vast sheet of trampoline rubber. When a massive object like the Earth sits on that fabric, it creates a dip. But when an object spins as fast as a neutron star or a black hole, it doesn't just sit there, It grabs the fabric of space and time and twists it. Imagine placing a heavy, rotating drill bit onto that trampoline. The rubber wouldn't just sink, it would start to wrap around the bit, creating a swirling whirlpool in the fabric itself. This leads us to the deepest complication of the extreme layer, the black hole. While neutron stars are made of matter, a black hole is a region where the gravitational collapse has become total. Almost every black hole we have ever detected is spinning, and they do so with a violence that liquefies the laws of physics. Around a spinning black hole, there is a region called the ergosphere. The ergosphere is a no-man's land outside the event horizon. It is a place where space-time itself is being dragged around the black hole so forcefully that the very concept of standing still is quite literally illegal by the laws of physics. This is a difficult concept to visualize, so let us place you inside it. Imagine you are in a high-powered spacecraft hovering just above the edge of a spinning black hole. You point your engines in the opposite direction of the hole's spin and fire them at 100% capacity. In any other part of the universe, you would move away. You would be stationary relative to the stars. But here in the ergosphere, your engines are useless. Even at full throttle, you would be dragged sideways. You are not moving through space. The space you are currently occupying is itself moving. The fabric of reality is turning faster than your engines can resist. In this region, the direction of forward in time becomes mathematically linked to the direction of the black hole's rotation. To try and stand still would require infinite energy because you would be trying to fight the flow of time itself. This is the extreme layer of spin. It reveals that the universe is not just a stage where things rotate. The stage itself is a participant in the dance. We have measured this drag on space-time directly. In 2004, NASA's Gravity Probe B experiment used ultra-precise gyroscopes in orbit to confirm that even the Earth, which spins quite slowly compared to a black hole, drags the fabric of space-time by a tiny, measurable amount. If our quiet, slow planet can twist reality, imagine the chaos at the center of a galaxy. But this raises a final, haunting question for this chapter. If rotation is powerful enough to twist space and time, what is holding the largest structures in the universe together? When we look at the way entire galaxies spin, the numbers stop making sense. According to everything we have discussed so far, the fastest spinning galaxies should be shattering. They should be flinging their stars into the void like water off a wet tire. The fact that they don't tells us that there is an architect we haven't seen yet, an invisible force that is making sure the cosmic machine doesn't fly apart. If rotation is powerful enough to twist space and time, it should be powerful enough to destroy a galaxy. As we move from the violent, localized whirlpools of black holes to the grand, sweeping scales of the entire cosmos, the mystery of spin takes on a different, more haunting character. Up to this point, our investigation has followed a logical trail. Mass creates gravity, gravity pulls matter together, and the conservation of angular momentum forces that matter to turn. But when we apply these confirmed laws to the largest structures in the universe, the math stops working. The universe is spinning too fast for its own good. To visualize the problem, we have to look at an analogy from your own childhood. The playground merry-go-round. Imagine a massive wooden merry-go-round. At the center, near the iron pole, the rotation is easy to manage. But as you move toward the outer edge, the centrifugal force grows. You have to grip the railings tighter just to stay on. Now imagine that merry-go-round begins to spin faster and faster. Eventually there is a limit. There is a point where the wood would splinter, the bolts would shear off, and you would be flung into the grass by the sheer violence of the velocity. Every spiral galaxy in the sky, including our own Milky Way, is currently spinning far past its breaking point. According to the laws of gravity established by Newton and Einstein, the stars on the outer edges of a galaxy should be moving slowly. Just as Neptune crawls in its orbit compared to the frantic speed of Mercury, the stars furthest from the galactic center should feel a weaker pull of gravity. They should be drifting, instead they are racing. This brings us to the historical backstory of the most important law gap in modern astronomy. In the 1970s, an American astronomer named Vera Rubin began measuring the rotation curves of spiral galaxies. A rotation curve is a technical term for a simple graph. It plots the orbital speed of stars against their distance from the center. Before Rubin's work, the established data predicted a Keplerian decline, the idea that speed would drop as you moved away from the center of mass. But as Rubin looked at the Andromeda Galaxy and hundreds of others, she found something impossible. The curves were flat. The stars at the very edge of the galaxy were moving just as fast as the stars near the core. This is not speculation. This has been measured directly by multiple independent teams for decades. Rubin's discovery presented a terrifying complication. If these stars are moving that fast, there isn't enough visible gravity to hold them back. Based on the starlight we can see, the gas we can measure, and the dust we can track, every galaxy in the universe should be shattering. They should be flinging their stars into the intergalactic void like sparks flying off a grinding wheel. The fact that you are here and that the Milky Way still has its elegant spiral shape means that something is missing from our map of reality. There is a dark architect holding the machine together. To understand the resolution to this mystery, imagine you are standing in a field at night. You see a heavy stone orbiting a point in the air. It is circling at a high speed, defying gravity, yet you see nothing connecting it to the center. There is no rope. There is no wire. Your brain would not conclude that the stone is magic. You would realize that there must be a string. It is simply made of something you cannot see. This is the birth of the concept of dark matter. Dark matter is the invisible rope of the universe. It is a substance that does not emit light, does not reflect it, and does not absorb it. It is featureless. It is silent. Yet it possesses mass, and therefore it possesses gravity. This is confirmed science. The data shows that galaxies are not just collections of stars. They are tiny islands of light trapped inside massive invisible spheres called dark matter halos. The scale of this invisible architecture is difficult to comprehend, but we can look at the numbers. Everything you have ever seen, every star, every planet, every person, every atom of gold in a wedding ring makes up only about 5% of the universe. Dark matter makes up roughly 27%. The rest of the universe is held together by an architect that refuses to be seen. Without this invisible mass providing extra gravity, the twist of the universe would be its undoing. The rotation we inherited from the Big Bang would have torn the cosmos apart before the first life forms ever had a chance to emerge. We are living inside a massive contradiction. We are held together by a ghost, but this leads us to the deeper layer of the law. If 27% of the universe is this invisible matter, what is it doing? Recent studies of the cosmic web, the largest known structure in existence, suggest that these dark matter filaments are not just static ropes. They might be turning. We are beginning to see hints of rotation on scales of hundreds of millions of light years. Entire rivers of galaxies might be spinning along the long axes of invisible dark matter threads. This means that spin isn't just a property of objects, it is a property of the skeleton of the universe. But as we look at this dark architecture, a new unease sets in. If the universe spent the last 13 billion years building these magnificent spinning machines, these galaxies held together by invisible hands, what happens when the machines begin to run out of energy? We have established that once a twist begins, it cannot be destroyed, but it can be stolen, it can be leaked. Even as we sit here, the Earth is losing its spin. The Moon is stealing our momentum, and the galaxies themselves are drifting toward a future where the music of rotation finally begins to slow down. Everything we have discussed today leads to this final realization. The universe is a machine that is slowly running out of rhythm. Right now, as you sit in your chair, the very ground beneath you is losing its momentum. This is not a metaphor. It is a physical, measurable reality. Earth is slowing down. Specifically, our planet's rotation is decelerating by roughly 1.7 milliseconds every 100 years. 1.7 milliseconds. To your brain, that number is invisible. It is a fraction of a second, so small that it could never be felt within a human lifetime. But in the architecture of deep time, it is a tectonic shift. This is confirmed science, measured by comparing modern atomic clocks with the ancient records of solar eclipses carved into Babylonian clay tablets. The data tells us that 400 million years ago, during the Devonian period, when the first life forms were beginning to crawl onto the land, a day on Earth lasted only 21 hours. The year was not 365 days long, it was 410. The planet was spinning with a frantic, youthful energy that has been steadily drained away ever since. The thief responsible for this stolen motion is the Moon. As the Earth spins, the Moon's gravity pulls on our oceans, creating what we call tidal bulges. Because the Earth rotates faster than the Moon orbits it, our planet actually pulls these bulges ahead of the Moon's position. In response, the Moon's gravity tugs back on that bulge, acting like a giant, invisible brake pad. If you take your hand and lightly press it against the edge of a spinning pottery wheel, you feel the friction. You feel the wheel fighting to keep turning against the drag of your palm. The Moon is that hand, but in physics, momentum cannot be destroyed. It can only be transferred. As the Moon steals Earth's rotational energy, it uses that energy to push itself higher. The Moon is moving away from us at a rate of 3.8 centimeters per year. 3.8 centimeters. This is roughly the same speed at which your fingernails grow. It is a domestic, quiet pace, but it means that every year the celestial dance changes. The Moon is retreating into the dark, and as it does, it drags our planet toward a state of total stillness called tidal locking. Eventually, billions of years from now, the Earth will stop rotating relative to the Moon. One side of our planet will be locked in a permanent gaze with the lunar surface, while the other side will never see the Moon again. The 24-hour cycle will be gone. The rhythm that has defined every biological process in history will finally cease. But this slowing is not unique to us. It is the destiny of the entire cosmos. As we look deeper into the void, we see the same leak occurring on a galactic scale. We have measured magnetic braking in stars, the process where solar winds carry angular momentum away into the vacuum, causing stars to spin slower as they age. We see elliptical galaxies, which are the ancient graveyards of the universe, where the organized, beautiful spin of spiral galaxies has been cancelled out by violent mergers, leaving the stars to move in random, still orbits. The universe is moving toward a state of heat death, a future where the gradients of energy and motion have all been smoothed out into a featureless, cold equilibrium. Yet there is one final passenger in this investigation that refuses to go quietly. Long after the last star has flickered out and long after the last planet has been swallowed by the dark, the black holes will remain. These are the final engines of the cosmos. As we have established, almost every black hole we have ever detected is spinning at a significant fraction of the speed of light. But even these titans have a deadline. Through a process known as Hawking radiation, black holes are slowly, imperceptibly evaporating. They are shedding their mass and their energy into the void. This leads us to the most profound complication of our entire investigation: the information paradox of final spin. If a spinning black hole, an object that has carried the angular momentum of 1,000 dead suns, evaporates into a featureless cloud of radiation, where does that spin go? Angular momentum is supposed to be conserved. It is a fundamental law of symmetry. But if that final black hole dissolves into the dark, it may take the last memory of the universe's first twist with it. It is the possibility that at the very end of time, the universe's oldest secret, its original motion, is simply deleted. This leaves us with a state of honest uncertainty. We do not know if the total spin of the entire universe is exactly zero. Multiple independent teams have searched the cosmic microwave background, the afterglow of the Big Bang, for signs that the whole of space-time is turning. So far, the results are inconclusive. We see hints of a handedness in the galaxies, a 1% preference for one direction, but the scale of a universal rotation remains hidden from our instruments. Some theorists speculate that we are simply too small to see the curve. They suggest that our entire observable universe might be a tiny, spinning bubble inside a much larger, rotating multiverse. In this view, our 13-billion-year-old twist isn't an accident. It is an inheritance from a parent cosmos that has been turning forever. We are forced to confront a reality that is both immense and indifferent. The investigation into the why of spin may never reach a clean resolution. We are a species that has only been measuring the stars for a few thousand years, trying to decode a choreography that has been unfolding for billions. But there is one thing we can say for certain. You are not an observer of this motion. You are a participant in it. You are a living record of a 13-billion-year-old twist. The atoms that make up your body were forged in the centers of spinning stars. The left-handed molecules of your DNA carry the same directional preference that was written into the laws of subatomic physics at the dawn of time. Even as you feel perfectly still, the world beneath your feet, the blood in your veins, and the electrons in your brain are all dancing to a rhythm that was set before light even existed. The universe isn't just moving through space, it is remembering its own origin through rotation. Every turn of the Earth, every orbit of a moon, and every spin of a particle is a continuation of that first, primordial nudge. You are a part of that memory. You are a small, brief heartbeat in a cosmos that refuses to stand still. And in a universe this vast, this strange, and this beautifully persistent, that is the most interesting thing we can know.